Well, let's get started. I'm pleased to introduce the presenter for this webinar, Jim Hauer, Danfoss Sales Director of our Industrial Refrigeration segment. Jim has been with Danfoss since 2006, holding a variety of positions from technical and engineering to sales and management. Jim?
All right, thank you, Michael. Thank you all for attending the webinar. This is something that we try to do quarterly, whether it's from a product focus or an application focus. We do try to keep up with these. Danfoss is kind of known for putting out a lot of new products and innovative products, so we tend to have quite a bit of information to send to the marketplace. We will try to have another one of these pretty quickly, but if you were at RITA, you've seen that Danfoss was able to come out with 2 new products at the RITA Expo. One was this ICFD that we're going to go over today, and one is a 2-step solenoid, and they both kind of work in conjunction with each other. There's a lot of information on the ICFD and this defrost and just defrosting method, so we're going to focus on that in this webinar, but do look forward in the future for having another webinar coming up soon for the 2-step solenoid. So overall, anybody in industrial refrigeration does understand that defrosting is a necessary evil, let's say. We are in the refrigeration world. We're here to keep things cool and cool down spaces. So adding in heat to a room is kind of detrimental. So we do it as little as possible, but yet we aren't very good or very sophisticated about it. We need to defrost because as the air is blowing across our evaporator, it's changing, and then the moisture is then attracted to the evaporator, and if it's below freezing, it's freezing on the evaporator, which is then insulating the evaporator thins and hurting heat transfer. So overall, evaporator defrost is something that we have to do to remove the ice from the evaporator to allow for an effective refrigeration system. That's something that has to be done continually throughout the day or throughout the year. But within industrial refrigeration, if you've been to a lot of different plants, it's something that's not done very scientifically. It's something that's done pretty arbitrarily. There's not a lot of actual sensing elements to it traditionally. And it's something done with a lot of timers and clocks and guesswork, and something that isn't very well looked after and maintained. So there's a lot of potential in the industry to save money, save efficiency when looking at this. Overall, if you look at the industry, the vast majority of the industry is defrosting with hot gas. There's many reasons for it. If you've been to IIR and been to RITA, you've listened to many different consultants. There are various different ways to defrost, whether it is hot gas, which is what we're going to talk about today, or electric, or water, or a glycol coil. Each one has its specific pros and cons, but the industry has more or less settled on hot gas defrosting. 90+% of the industry is defrosting with hot gas defrost in one way or another, and that's because of a mix of install cost and energy optimization and efficiency. It is seen as the most efficient way to defrost your evaporator overall is with hot gas. But kind of as we'll demonstrate today, not all hot gas defrost systems are created equal. If you think about a traditional plant, this is what we tend to see. Especially previously, most of the plants running out there built more than 10 years ago. You see individual components on your liquid line, your suction line, your hot gas lines, etc. Very typical pump liquid evaporator is kind of what's on the screen. And then you will have a single hot gas defrost line. Sometimes it will go through the pan first. Sometimes it will be in parallel with the pan. In this case here on the picture, we're actually doing defrost a little bit smartly by injecting into the hot gas line with an ICM motorized valve. So we're metering in the hot gas in this case. But in most cases, we see that it's just a simple hot gas solenoid valve. And then for defrost relief, you can see teeing off the liquid line and feeding into the low temp suction is a ICS pressure regulator with some SVA shutoff valves. This is what in this presentation we call pressure control method. This is very typical to what a large portion of the industry is doing for hot gas defrost. And it's what we've seen, especially more than 10 years ago, was individual components. Danfoss has come a long way in helping the industry, both from an efficiency and effectiveness from construction to service. Most of new construction and retrofit opportunities, repiping, is kind of shifted to valve stations. Not just Danfoss job site installations, but we see the whole industry and valve industry going towards valve stations. And Danfoss has led that way. We were the first to have them, and we also have the largest valve stations now going through 2.5 inches, and with motorized and hot gas. So we can see we've been able to do a lot in helping contractors and end users quickly install and having a nice system to service and something that's really efficient. But you can see that while we have a liquid line that is and a hot gas and a suction line that has a valve station, we still have this pressure-controlled, non-valve station defrost relief line. And there's been a push from the industry saying, when are you going to have a solution here for a defrost relief line? And it's something that we've wanted to do for many years. But with most of the Danfoss portfolio, when we make a investment in the portfolio and the industry, we don't want to just copy and paste maybe the standard of what the industry is. We want to improve upon it and really add technology and add efficiency and effectiveness when we can, incorporating those into features. And that's what's taken us a while, but we think we have a really great product that we're going to show you here. So when we take a look at what the industry was, which was this primarily hot gas defrost with pressure control, pressure regulators. It's the most common out there, and the reason it's the most common is because it was easy to do, relatively low cost on the install side, and it was reliable. If you ran your defrost often enough, long enough, you had a clean coil. What we've seen, though, is it's not very efficient. It's very efficient in the time that it's necessary. But what we see is so many job sites, whether it's because of contracting and using, maybe differences changed, maybe things weren't maintained. We see defrosts that are far too long and far too off, and maybe done by clock, where we see, your defrosting needs in the summer are many times in many parts of the country vastly different than what they are in the winter. So we see that the pressure control method is one that could really be improved upon. And all of that excess hot gas going into your evaporator and then leaving your evaporator non-condensed, going through your defrost relief, has adverse effects on the refrigeration system. And the industry's answer to that has been a traditional solution, which is float valves. Float valves aren't new to the industry. It's something that has been around for a very long time. It's a tried and true method, but it isn't very popular. Even though it is widely accepted, and there's been multiple papers at IIR and RETA, multiple papers by professional consultants saying float valves are a highly efficient way to defrost and increase efficiency in the existing installation base. But there's reasons that they weren't adopted in the industry. One is initial cost of the products, install cost, and design flexibility. Did they have lifting height requirements? They were maybe a little bit tough to tune in the contracting world because there was the idea of different lifting requirements. Did they have the bypass? Was the bypass set correctly? And just cases where the industry wasn't very familiar with them and they were an expensive solution. So in a design build world, they weren't always utilized maybe as much as they should. So what we've done is we've taken what is a tried and true method that we've seen proven, and then we've tried to improve upon it and adopt it into the product line here. And what we've done is we've seen that the float valves stop the hot gas from recirculating. It ensures that only liquid condensate goes back to an intermediate vessel or your recirculator vessel. It's highly modular from the standpoint that it self-adjusts to capacity and overall is a big energy savings. So taking a look at it, I mean, the main difference really is that a pressure control valve, whether it is liquid or uncondensed hot gas, will bypass back through the suction or back to your intermediate. So once you hit that pressure control set point at 75 or 80 psi in the ammonia world, which is most where the regulators are set to, a mix of liquid and hot gas is then being sent downstream. And we see that that mix changes during the length of the defrost. So maybe in the beginning of the defrost, you're condensing quite a bit of liquid, and then you're sending mostly liquid back. So at the beginning of the defrost, you might be quite efficient, but at the end of the defrost, you're blowing all of that excess hot gas right back out. Where the liquid drain is adjusting throughout that defrost, and because the liquid float is rising and falling, it's sending only liquid back. And then when very little liquid is coming back from the evaporator and it's not allowing the float to rise, essentially we're not bypassing any hot gas, which is the efficiency gain. And here's a real pictorial about this. I'll give some more further into the presentation about this, but we've done both a theoretical analysis and a actual analysis across multiple plants, and we see there is a big efficiency gain here to be had. Where on the liquid drain method, you can see that since it's only moving this small portion of liquid, it's a very efficient method to do this defrost, where we see the blow-by hot gas overall is overheating evaporators, which is adding extra heat into the space. When you're doing that, it's also then having that moisture go back into the air, which will then come back onto the evaporator in the form of ice, causing you to defrost again, which is one of the things we're trying to avoid. And that blow-by hot gas is then just going straight back to your compressor, making your compressors work harder and adding false load, essentially. So this uncontrolled there's a lot of different byproducts when you have this blow-by hot gas. And this is kind of what we see in terms of a time of a evaporator defrost. When you're at the beginning of an evaporator defrost, which is the left side of this picture here, whether it is pressure control or whether it is a liquid drain method, they use the same hot gas solenoid valve arrangement. So if it needed a 1-inch hot gas valve, it's going to have a 1-inch hot gas valve, whether it's pressure control method or float valve method. And they all have the same CV value. So therefore, when you start a hot gas defrost, it's going to start the same. But then as your evaporator starts to warm up and that ice decreases and that heat load changes, and then you're not condensing that hot gas being ejected into the evaporator, that's where really you see this big difference. And that difference is changing every time. It's very variable. It depends on your load profile, how much moisture is in the air, how much moisture is coming in or out of the products. It's different for a dock unit that might be in the summer versus winter. So this is where we see that it's very hard to be super precise on when to defrost unless you have very sophisticated sensors that are defrost on demand, looking at frost sensors and things like that and runtime. we see setting defrost is still a problem in the industry. So this is one way to ensure an efficient defrost while still remaining mostly mechanical. So what we've done is we've been able to map some of what this is and where does this energy go. And this is what we've tried to show here with maybe different size evaporators and different lengths in terms of time because all of our defrosts are still mostly time terminated, and like I said, they're not defrost on demand or having frost sensors. The vast majority of the industry is running off of timed defrost and that time terminated. So this is really where we see you know, the losses, and it's not only this blow-by gas, which is false loading compressors or heating up a whole vessel of refrigerant. There's also convection loss, coil heating, ice melting, and where is this energy that we're injecting this hot gas? Where is it going and what is it being used for? You can see one of the biggest things is, you know, 24 to 38%, and this was reality, these were actually tests, was blow-by gas. So we weren't even using a large majority of the hot gas that we were entering. The thing that we were doing, and the reason we need to defrost, is this ice melting and ice heating. And you can see that that's only a small portion of, you know, the percentage of the hot gas that you're entering into the evaporator, especially in the pressure control method. And what we've been able to do is then inject that much less hot gas into the units by, once the float valve closes, the evaporator will come up to essentially the hot gas head pressure, and then therefore the valve will no longer feed anymore. You can see that even under the liquid drain method, even though it is float valve, there is 3 to 5% blow-by gas. We will show you why that still is in a float valve when we get to the valve design. And this is the big thing, is that, you know, that blow-by gas essentially is false loading your compressor. So therefore, it ends up increasing the load on your compressors, the runtime on your compressors, and the size of your compressors when sizing them. So there's multiple issues when it comes to the blow-by gas. And having an efficient defrost that is defrosting less often and not blowing by that hot gas just contributes to a system that runs that more efficiently, effectively, steady state, not loading, not ramping up and down. So, and what we see is that it is a large difference. Again, we'll show you some of these numbers. We actually have a 23-page white paper. I'm not going to go over all 23 pages of that. I'll just go over some of the highlights. But at the end of this meeting, we'll in the invite where we email everybody out who requested to attend, we will give that 23-page white paper to you guys. So that way then you can see the data behind it. Because most of us in the industries are all engineers. We like to see the data. We like to see, well, hey, what were they paying per kilowatt? Where did they put sensors, et cetera? How did they measure this? So we put quite a bit of time and effort into the white paper and the data crunching behind this. But we see it is a very big savings. You know, from a very high level view, if you have a nominal electricity rate, and if you went from a standard, let's say, evaporator defrosting method, you know, time defrosting once per day, defrosting taking 20 minutes, et cetera, you were saving a $1 per defrost per evaporator. It really, if you do a lot of averages, that's kind of where more or less you end up. So it's quick. If you have a 25 evaporator plants and you're defrosting twice per day, it adds up very quickly, and we see it is a quick payback to install float valves. And that's where we see the liquid drain method was really what to focus on rather than making a pressure regulator into a valve station in these small sizes. We saw if we could try to create a liquid drain method in a valve station, it could really help the industry move forward with being able to control efficiency. And it reduces overall operating costs. And it's something that's actually, from a contractor perspective, even though contractors aren't necessarily first concerned about operating costs, it's something that's easy to install, it's self-adjusting, it's there for a wide range of tonnages, and not just for different tonnages of an evaporator, but we can see this specific application, your tonnage requirement changes as you defrost. So you're passing a lot of liquid when you first start a defrost. You might be moving 40 tons worth of refrigerated worth of liquid, where at the end your flow trickles down as you've defrosted that unit to where you only have a 5-ton load. So this has actually been a challenging pressure application for a pressure regulator. And when we walk the roofs, we hear it and we see it. This is a spot where we see pressure regulators chattering, and we talk as an industry about oversized pressure regulators, especially in this application. So having a liquid drain method was something that we saw was an ideal situation to try to move the industry forward in solving some of this. So this is what the product does look like. If you were at RITA, you saw this in the valve stations on our new valve display. If you're part of our mailing list, you've seen some communications on this. We actually have a several-minute video on this that we've produced, but this is what the product looks like. And one of the first things you see is that it's attached to a valve station. This is what we really wanted to do. The industry has accepted valve stations. They now basically prefer valve stations by default, both from a contractor standpoint, price-cost competitiveness, speed of installation, service at the end user, etc. So what we did is we took all the benefits of a valve station and found a way to incorporate a float into it. And it's in our existing valve station. So overall, we liked that. It allowed us, we saw the valve station as a proven model and a proven concept. At this point, we've now have over 60,000 of them installed. So the industry is used to them. And this is something that then it allows us to use our existing stop valves and allows us to have a lot of different options and flexibility. If you want a solenoid with it, if you want a check valve with it, it allows us to use all of those existing flexibilities in the valve station with this float valve. So this is then what it looks like with our common evaporator with the new defrosting float method. You can see that we've replaced the pressure control, and now we have a valve station, which is easier and simpler to install and operate, and now with this float. We'll get into some of the application and design requirements. We can see that in the liquid line, it is trapped before going up to the defrost relief float. There is a riser, and we can get into some of those specifics. But it makes for a nice clean installation, and it also matches well with the ICF in the suction line, because the ICF in the suction line has that defrost drain connector right in the side of the valve station and that union assembly. So that way then you don't need to actually tap into your suction line. You can just tee straight into your valve station without tapping into the suction line. Makes a really nice clean installation. So taking a look at this, what we've done is we've been really able to make the job site more efficient by having that valve station from a construction standpoint. It's a broad application range. You can get this in, like we said, the ICF, but not only the ICF 20-4, which is the 4-module valve station, so that might be 2 stop valves and a drain. You can get in the ICF 20-6 if you wanted 2 stop valves, a drain, and a solenoid and a jacking stem, or maybe a check valve. And then even that ICF 15-4, which is that really compact one where maybe you have half-inch lines. This makes a good use for maybe when you have the end of a header or a small glycol floor warming application. What we've been able to do is incorporate it into all the Danfoss tools. So if you're familiar with our Coolselector sizing software, you can already see, if you've been on Coolselector lately, it already has the ICFD and defrosting sizing now incorporated into it. I have a few slides at the end of the presentation on it. But it's incorporated into the Coolselector sizing software. It's incorporated into our DIR quotation software. So it's part of all the Danfoss tools. So getting into a little bit of the design meat, it comes in the ICF 20. We do not have a increased size. With moving to the ICF 25, we see that there's enough capacity in this defrost module that we probably do not need to step up to the size 25 at this time. We think we can address the majority of the evaporator sizes in the marketplace, all inside of this ICF 15 or 20 housing, mostly on the size 20. Overall, because the ICF 20 comes in a 3/4 inch, 1 inch, and 1 1/4 inch connection. So that covers all a large majority of the connection sizes in the defrost relief size. You know, and from what we'll see, so anywhere between a 5-ton and a 55-ton unit, give or take, is the capacity of this defrost drain. Some of that is dependent on the temperature it's connected to, the riser height, and some other specifics, which we will quickly highlight. But more or less, 55-ton units and down is the vast majority of the market. So this is going to allow us to apply this into 90+% of the applications, all in the ICF 20 housing. So this is a nice cutaway of it. It is a patented design. Danfoss has a couple patents on this. It is a mechanical float, very traditional float style assembly. You can see when you're starting to look at this, you can see the inlet flow and outlet flow are very close to each other. You can't quite see in the cutaway. You would almost need to be a 3D model. I was having a little bit of trouble finding a quite way to pictorially show this. But essentially, in the middle of the module will be your return, your defrost return. That liquid and gas mix will come down and into the float chamber. If the chamber level is rising, that will then allow a passageway around the outside of that inlet flow tube for that gas to be ejected out of the module and then go into the top of the valve station and out the outlet of the valve station. And you can see off to the side is this bleed line and bleed orifice. This is this 3% or 5% bleed in blow-by gas that we saw on those previous pie charts. This is a necessity for a float valve, and that is because of the riser itself. And is indicative not just of the Danfoss design, but float valves that we see across the industry. And that is because if you have a riser filled with vapor when you start a defrost and you want to then move the liquid up the riser to get to the ICF valve station, that vapor has to go somewhere to get that liquid to push up. So this is a bypass bleed for that vapor to be pushed, for the liquid to push the vapor up and out the bleed orifice. So that way then the liquid can start the flow of the defrost cycle. This is very common to the industry. Actually, typically we see these as an external bleed and as an external bypass, and that's something that requires extra valves in the industry and has to be manually set in the field. So the fact that we've been able to incorporate it into the float design itself, and it's only a very small orifice, 1 or 2/16 of an inch, it's very nominal, and it's actually quite a bit smaller. If we look at the typical industry insulation, we're installing a 1/2 inch or a 3/4 inch hand expansion valve as a bypass bleed. So the fact that we've gotten this down to an 1/8 of an inch line is very reasonable. So this gives some of those specs. Like I said, nominally up to a 55-ton evaporator unit. Riser height does have an effect on evaporator capacity. Our max riser height that we're recommending right now is 16 feet. So that's mostly for ceiling hung evaporators. If you have designs that are essentially penthouse units, it's not a portion of the calculation. But if you do have ceiling hung units where the valve's on the roof, this does become a factor. But we think that 10-foot riser is pretty normal, and we can go up to a 15-foot riser before it really starts to have a detrimental effect on capacity. Max working pressure is 400 pounds. And this is something that is important because if we know and understand the Danfoss valve portfolio, we tend to have one specification, which is 750 psi. Good for ammonia, good for CO2, good for all refrigerants. And here we can see max working pressure for this module right now is 400 pounds. So that means we're going to be using this for ammonia only right now and not a CO2 relief. We are working on a CO2 variant because we see all the same benefits for CO2 installations, and Danfoss is kind of the leader in CO2. So we do want to create a variant for CO2, but that's something that's not quite released yet, and that's going to be because of the pressure of CO2. Unfortunately, we can't do it all in one module, so we're going to have a different module for ammonia and CO2. But ammonia is 90% of the industry, so this is what we wanted to focus on first. So here we can see it's a nice, very simple installation once again. Here it shows all the different variants of ICF, and it shows all the different types of control that Danfoss does. Mechanical floats, hand expansion in liquid, motorized hot gas, and having two-stage hot gas in the suction. Two-stage gas-powered valves in the suction. So overall, it's very flexible from the standpoint of it can be configured different ways in the ICF-20. It does allow for a vast majority of capacities, both from within defrost and for different units. That's kind of that automatic capacity adjustment. And we can show here in some slides that also helps lower the charge overall of your refrigeration system. The big thing is that it has a quick drain capacity. That was one of the concerns that we did have in designing this, is that we know in the industry pump outs aren't always done optimally. We still request that it's something that's done as part of commissioning and as part of your refrigeration cycle is to do a refrigeration pump out. But we see that in order to get a quick defrost, we need to evacuate whatever liquid is left in that unit. So we did want a high float capacity. That way then whatever liquid is left in the unit or at the beginning of defrost, we can pass a lot of condensed liquid through the float and into the suction line. And we're able to do that with a pretty good CV value, actually. And it's for compact, pound for pound, it's bigger than most floats on the market. If you remember and are familiar with our other Danfoss product lines, the HFI float valves and that big 4- and 6-inch connection and that float ball inside there, this is actually the same capacity as some of the smaller orifice sizes of that big HFI float. So it allows to pass quite a bit, which is allowing for not only efficient defrost, but very quick, which is important, especially during food production. Because it is a float, overall, when it is closed, it's not something that chatters. So this allows us for a high variability of being able to handle a lot of different capacities, 5-ton units, 10-ton units, 20-ton units, and then the different phases of the defrost, beginning of defrost, end of defrost. And this is where we're getting into charge. Overall, it's allowing to have less liquid sitting around. There's not a lot of liquid just sitting, bypassing in the bottom of the evaporator. And that's one of the things we actually saw too, is we saw that during defrosting with pressure control sometimes, depending on how the evaporator was piped, we saw a lot of different liquid just sitting in the bottom of evaporators, and then that was then also stopping those lines from defrosting. So using a float method, having a bottom drain allows for a faster defrost, more efficient, more even across the evaporator, and a lower charge. So overall, then when we're sending only liquid back to, it allows us to, and having a more stable system allows you to kind of trim your charges in your vessels. It is possible, if we think about floats, and traditionally, because people were concerned about risers and riser heights, we saw a lot of floats installed at the bottom of the units, down at the evaporator rather than up on the roof, which is harder to service. And it's another gasket and another leak potential that's sitting in a space rather than up on a roof where it can be serviced and out of the way. We've done quite a bit of testing here. We can handle a liquid riser. That riser must be trapped, so that way then we have a constant liquid flow going up to it. But that riser height can be as much as 15, 16 feet. And overall, it's pretty flexible because it is in that ICF 20 housing. Can be mounted in different configurations with or without solenoids, with or without check valves, all the way up through 58 tons. No adjustments are needed. You don't need to adjust that bypass hand expansion. Overall, all you're doing is removing a rod that we use to keep the float from banging around in transportation and install a drain valve. And it's ready to go. It actually does have a manual jacking stem on the side of it. On the bottom ICF, on the bottom right, you can see that little red circle. That is actually a manual jacking stem, so you can manually open this when you do need it. You can also see that part of the flexibility is you can adjust the direction of that float. It doesn't change the design or the capacity in any way. It allows you to just rotate or clock that float out of the way. If you have your liquid line, hot gas, defrost relief, all piped in parallel, this allows you to keep nice clean spaces for the service operator in between all the different headers. So some of those design requirements, I've already touched on them some, but it does require some upfront forethought. And the one that we already have talked about is this liquid riser lift. It does need to be lifted. This liquid does have to get to the roof to then operate the float. So we see this 15 feet limitation is what we want to start with. We're going to continue testing to see if we can push that limit. But we see 15 feet as covering the vast majority of ceiling hung evaporators. So what we also see and what we've also touched on is this gas-mounted bypass orifice. People familiar with floats, are probably looking for the bypass. This is one that we're going to show the industry that it can be done internally, so that way it's something that they don't have to test. Because it's not a big hand expansion valve bypass, we're bypassing even less than the traditional floats of the industry. So here you can see, this is also in Coolselector 2, but as a chart form, you can see that the liquid riser height does have an effect on tonnage. So a nominal 50-ton evaporator unit, will reduce to a 40 or even 30-ton if you have the maximum liquid height, riser heights. So this is where we're saying trying to keep them reasonable, but we can do quite a large span still. And this is the other one that we do have to remember, and I have touched on already, is the importance of traps and having a trap on that riser. We do like to see traps on the suction line for various reasons, for oil return, especially in DX and other items, but also on the liquid defrost relief line. That is an item that needs to be trapped, so that way then it does get the liquid flowing back and up the riser and up. Because if you do not have the liquid trap, the hot gas will flow up and the vapor will flow up, but it can't capture and carry that liquid slug and move that up. So it either needs to be a single liquid riser, which is the middle picture, or have a double riser, as in the bottom picture, and then have a full-size liquid line and then a intermediate size defrost relief riser. So we can work with multiple types of coils. Overall, the main requirement is that the liquid feed must have a bottom-mounted drain connection. So that way we're draining out the bottom of the evaporator and the trap's coming off the bottom of the unit. We see across the globe there is different types of configurations, top feed, bottom feed, and kind of even a hybrid side feed. You can use multiple of these variants, but the riser for the defrost relief needs to come off of the bottom feed. And one other thing to think about, now that we've replaced your pressure relief valve with a float, depending on what you have in the suction, you may not have a way to relieve excess hot gas pressure. And that depends on what's going on in the plant. Do you have a King step-down hot gas outlet pressure regulator, so that way you have an intermediate pressure rather than full header pressure out at your evaporator units for hot gas defrosting? What kind of suction control do you have? Is that motorized? Is that gas powered? Or is it a pressure regulator to start? If you do not have a pressure regulator, this is one thing to think about. The main thing, in order to keep from overpressurizing your hot gas into your units, is we do recommend either having this King hot gas step-down outlet pressure regulator for the whole entire header of the unit, or stepping down that pressure at the units themselves, to avoid just having excess hot gas pressure inside of the evaporators. So this is kind of a checklist that we do have, because most of the industry has not moved to floats. So we think we're going to have to do a little bit of education of the customer base and work together on educating contractors, consultants on how to really properly apply these floats, because they weren't as common. So we have these in the PowerPoint. We actually have these as part of an application guide, a couple-page application guide that we've created to be released with the product. So these are some of the design considerations. So like I said, we've done quite a bit of time testing it, both from a theoretical standpoint and from a job site standpoint. We put a lot of time in testing, a lot of sensors into creating this, and having the white paper and the job sites to support this is a proven product that we've released. So what we've done is we've highlighted just we have more than this at this point, quite a bit more installations, since we've now launched the product at the RETA show and globally. But these are some of our first installations where we've done testing, and it's gone very well at all of these. A lot of good customer feedback. So here's some pictures of these products. The first here is a retrofit. So here is a freezer setup from Denmark, and this is one where we did quite a bit of testing. And this is very typical. We see a defrost was lasting 40 minutes, by timer, and it was defrosting every single day, regardless of whether it needed it or not. So this was a spot where we really saw a potential for savings, as we see most plants. And you can see below, here again, we're going to have the data as part of the white paper, so you can read it more in depth. But here you can see a vast energy savings by not bypassing all of that hot gas. Overall, we saw that they were saving 12.6 kilowatt hours, per defrost, 360 days per year, because regardless, they were just on time defrost every single day. And it saved almost $800 based on what they were paying on the kilowatt hour. So, and that was just on one unit in a year. So, till you have a whole evaporator plant of them, it was less than a 1-year payback. So here, a fish processing plant, once again in Denmark, 11-ton units, 17-ton units, did have a liquid riser, 3-foot liquid riser. You know, it was installed in an ICF 20. We saw that we had very quick defrost. They went from a very long defrost to something that they cut it in half almost, down to a 10-minute defrost. You know, very, very happy contractor, very happy end user. Here's a site in Germany. A little bit bigger unit, 20 tons, minus 40, so works for both coolers and freezers. 10-foot riser, defrosting depending once or twice a day. They were making adjustments throughout the year. You know, it solved a lot of icing issues on evaporator units, because that's what we see too, is not only, you know, is time defrost very popular, but they're not even looking, most of the end users and operators aren't even looking whether their units are defrosted and whether they have ice hanging on the bottom of them. So this is one where we saw they improved that. This is one in Mexico, 20-ton unit. And again, quick defrosts, again, because it's a nice size capacity. So that way then we can move a lot of liquid, because that's what we saw in the pressure control. Was that there was a lot of liquid left in many of these units because pump outs weren't optimal. So then you were spending a lot of time just heating up liquid, where this is you're evacuating it. So this is one of the spots where a quicker defrost is possible. These are just some of the job sites. We're starting up some job sites now where we have a few projects going on right now in the United States. We're ordering in right now. It's been a good success so far, a lot of customer interest. So like I said, we have been able to incorporate them into Coolselector. At this point, I don't want to take everybody's time and going into Coolselector screens. If you do have Coolselector, and every time you open Coolselector, it does update. So if you haven't been in Coolselector recently, you will get the request for an update. And it'll be a new section that'll show defrost relief and how to size not only these valves, but also still pressure control. Both of them are now incorporated into Coolselector. If you have any questions on Coolselector, feel free to reach out to myself, your Danfoss representative, your Danfoss distributor, etc. And then we can walk through those and walk you through Coolselector 2, its benefits, and also how to size not just this product, but our other Danfoss products. And then getting back to the white paper, you know, we'll distribute that white paper as part of the, you know, the end of this webinar. We'll send that email out as well as this PowerPoint with it in PDF format to everybody, so that way then it can be reviewed. If you have further questions, you can contact us. Feel free. And then here we can see across more than one units, across the units, it was a very quick payback. We've seen it. Typically less than a year, that dollar per defrost per unit, etc., at a reasonable, you know, kilowatt, even at less than 14 cents per kilowatt hour. When you're getting even less than 10 cents a kilowatt hour, you're still paying back first year. Because what we've been able to do is, kind of, since it's incorporated into a valve station, there's a lot of savings as well. So versus a traditional line, either with pressure control or with floats, when you have individual units, lots of welding, etc., there was quite a bit of cost. So incorporating it into the valve station has brought it closer to a low-cost pressure control method, and actually first cost, not only install cost, but even first cost versus almost all the floats on the market, we've been able to actually come in lower as a first cost than traditional floats. So it's very price competitive, and it's something that we're excited about. So this is, again, showing you know, some of what you will see in that white paper. The white paper goes into much more detail as to what we were measuring, how we were measuring it. But this is something then that's in the white paper that shows how to do the savings. That way then we can work with you on a calculated savings, you know, based on your kilowatt hour, you know, kilowatt cost, your tonnage of your units, how long you've been defrosting, how many defrosts you do per day. All right, couple minutes left. I tried to come in and go through this as quick as possible, so hopefully I haven't breezed through the details too much. I do see we do have a few questions that we will try to get. One of the first questions that I've gotten to is, if oil gets into the float module, do we risk clogging the bleed? Overall, this is one thing we have thought about. We do see that we should be able to pass most all oil through the outlet of this float. In the event that we do have an issue, maybe it's very cold oil, maybe very sticky oil, has a lot of contaminants in it going along with it because it's the bottom of the drain, we've actually incorporated an oil drain into it. That's where this transportation rod is that we do for the install. So to keep the ball from floating, from banging around during transportation when we're shipping the product, we actually put a float rod in there to secure the float. Upon installation, this rod is removed, and then you have a port which is then adapted to 1/4 inch, so that way then you can use a Danfoss SNV gauge valve in the bottom of the float as an oil drain if you do have a oil log system where it is not evacuating. So that is one that we have taken into consideration.
Another question we have is, when will it be available?
All right, like I said, we've launched this if you're a North America guy, you may have seen it at the RETA show or seen some of the emails, communications on it. So it is globally launched. It is ready for sale. We've already started to do our first jobs and first ship. Overall, we see that we're still building inventory, and there's a lot of demand for it that we're trying to keep up with. So we are producing right now. Right now, lead time is approximately 4+ weeks. Right now, we are on the plus side of that, and we are going into the end of the year here. So expecting January at the moment for new projects. Right now, we have quite a bit of projects going on. But getting into 2018, this is a stocked product for us. We will stock this product in multiple connection sizes and multiple variants, so it should be a 1-day lead time, like most all of our ICF is. And then with project size, you want 10 of them, you want 20 of them. That's our standard 1-week, 2-week lead time. All right, there's been another question. What have been the main issues associated with float drain method, and how does our design address those issues? I think some of the hesitancy on why the industry has not typically already adopted floats, even though that they know that floats are more efficient, is that, one, they were expensive, two, they weren't properly applied always by some installations, so then they had issues with riser heights or with logging in the evaporators, or not properly set bleeds or not having bleeds, so then they were having trouble getting them to operate. So, and it was very expensive to fix, where if you were wrong with a pressure regulator, you could just increase defrost time or change your port on your defrost relief. So that was something that could be easily masked, where in traditional floats, they were if you had a problem, it was an expensive install to resolve it, where we've tried to take a lot of that into account. We have the bleed built in, so that way there is a bleed. It's pre-adjusted. That way then it's kind of already built into the design. There's nothing to adjust, nothing to operate. We think we have a good flow rate. We have a good design in terms of that capacity control. And then with the application guides, we think we can help the industry apply these valves properly.
Another question is, what is the standard ICF defrost configuration?
Okay. Right now, today, the first ones that we're coming out with is stop valve, drain, solenoid, stop. And that is because we need the solenoid function, or else you would constantly be, when you're in refrigeration mode, bypassing your pumped liquid in the defrost relief line. So you need the solenoid to stop that. In the long term, what we're doing is we're developing a special high pressure, high differential check valve. So that way then you can eliminate the need for the solenoid. So that way then you can then not have that electrical point. The electrical point with the hot gas, with the solenoid feature, is a low install cost because that shouldn't be an electrical point from the PLC. You should just be able to put that in parallel from the junction box with your hot gas solenoid valve. All right, some other questions? Is there, trying to look through a few of them here, see if we get, I have a few duplicates, so. Is there a plan to go smaller or larger orifice openings in the future? Is there an MOPD to be aware of? We do actually have the potential to change and modify orifice sizes because what we've done is we've utilized, if you're familiar with the Danfoss product line, our AKVA orifices from the pulsing expansion valves, the AKVA 10 series, 10-1 through 10-8. Off the top of my head, I believe what's in there is a 10-5 orifice. Don't quote me on that. But overall, if there was an issue, and this could be a way to modify, if there was an extended riser, maybe longer than 15 feet, where you needed to try to push liquid and you needed to remove more vapor, this could be a way to modify that product, so that way then you could accommodate for that, is just switching to a different AKVA 10 series orifice. Hopefully I've answered that question then. Let me look through, see if we have any other good ones that we can do here.
Maybe we can answer 2 more questions.
2 more questions, all right. What about capacity relief to intermediate pressure, not low pressure? This is also one of the reasons why we want to have the check valve variant, because you're going to require a check valve to go back to an intermediate pressure. It doesn't have to be this high differential pressure check valve. It can be a standard one. So what we are creating in early is actually a check valve variant. So it will be a solenoid in check valve. So that way then it'll be the solenoids. That way you're not bypassing, but then you'll have the check valve there. That way you don't backfeed from the intermediate during refrigeration cycle. But then long term, like I said, we also will have this high differential pressure check valve variant. One last question is, the float valve have CRN for the Canadian market? And the answer is we have applied for it. We've applied for it in all provinces. We have to wait to hear back from every province individually, if you're familiar with CRN and how that works. It is by province, not just for one country. And then we have to hear back from every individual country. But we've used our partners and we've applied for it in every single country. And that was several months ago that we've done the application. So we expect to hear back very quickly. And we do hear back from most provinces in a 12 to 16 week time frame. So job sites for 2018 should be safe for CRN.
Okay. Maybe we have time to fit one more in.
All right. All right, let's, there's a lot of questions, a lot of interest. This is definitely interesting. One more, if there's liquid is drained from the defrost, is it really necessary to return to an intermediate pressure? And the answer is largely no. You know, and this is one of the benefits if you're on the design side, because if you're in a traditional design mode, you're using pressure control and pressure relief. One of the things we did as an industry was send that defrost relief, gas and liquid, back to an intermediate vessel. And putting it into the medium temp rather than low temp was mitigating some of the efficiency losses in the system. And now that you're returning only liquid, it really mitigates a lot of that difference. So therefore, the efficiency difference of returning it to a medium temp or a low temp is kind of negligible. So therefore, you can get quote-unquote 4-pipe efficiency with 3-pipe install cost. So that's a big install cost benefit, just going back to 3-pipe.
Okay, great. Well, everyone whose questions were not answered, I will make sure to write them all down, and we'll get back to you individually. In the meantime, I think that's it for today. Jim, thank you for your time and expertise and voice. I hope you don't lose your voice after all this. But and thank you to everyone who attended, and especially for your participation. So, as Jim mentioned, we have a couple of deliverables to you. As I mentioned, this meeting has been recorded, and you will receive the recording soon. So, yeah, thanks again, and have a great day.
Yeah, thank you all. There's a lot of clear questions. We do have your email addresses, so we'll capture these, and I will follow up with each one of these, and I will make sure I'll get you an answer on your questions. Thank you all for attending. This was really exciting. All right, look for these in the future as we continue. All right, thank you, everybody.
Bye.